of the presentation with the data assimilation. So we are going to the place where the data meets the equations through assimilation, which is very important for understand the data than only observe. A step 4, very interesting. We started with the first presentation by Rasmussen. Yes.
Yes. Thank you.
Very else.
Okay. Thanks. Hi, and thanks for letting me give this presentation. So my name is Silje Rasmussen from the Danish MET Institute. I'd like to go on to this one. And I'm going to present some work we've been doing on both setting the satellite observations in context with what's being modeled, but also trying to use the observations to correct and assimilate data into the models. It's not just my work. Jakob and Pia is here. I don't know if Chan is online, but others have also contributed. Yes. So I will give a short introduction to some of the characteristics of the different systems. We have both in situ observations, we have remote sense observations, and then the models. And then primarily on how the atmospheric models look at it and how this is transferred into the ocean and sea ice models, because there are some very distinct differences in these systems. And then I would like to take a look at the effect on some bias correction you can do based on the differences in the different systems, and what this impact not just on the surface temperatures, because of course if you change them they will change, but also on some of the thickness, ice thickness and others. And even though the session is on SST, this will only be on the ice surface temperatures, but Jakob was okay with that, so that's yeah. And these two images is from DMI, ocean DMI decay, and the top is the surface temperatures, the mix of ice and ocean temperatures, and the bottom is the difference compared to a climatology on the last 30 years, and the difference is very much based on weather systems passing by. So I wouldn't expect a real trend, which is also the case here. So what do we have? We have the in situ. These are sparse in time and space because you only have the buoys that are put on the ice and they drift around, floating with the ice and gets dropped off when the ice melts or is exported. And they are subject to a harsh Arctic environment, and often we use this as the ground truth, but as I will show later, that just a little bit of snow on top of a buoy will change the temperature quite a bit, and that's also have an impact on the truth. Or it's of course still the true temperature, but it's not the temperature where you want it on the surface of the snow or the ice. Then we have the remote sensing, which has a reasonably coverage. There can be some limitations in for instance, when there's clouds or other limiters. It still measures a signal that is converted to a temperature. It's not a direct temperature, so there's some conversion uncertainties, and I think many people in the room here are more familiar with that than I am. And then at last we have the models, which is solving some mathematical equations that ideally would solve everything you have up in this figure. And that's of course the case for all of them. It doesn't do that. It does some parameterization, some simplifications, etc. But this one tries to highlight all the different parameters you have within the system. And most important, and this is, I guess, for any observation model studies, always remember the limitations you have in the system and the of all parts of this. It's and take them as the best approach from each angle. Then in northwestern Greenland, DMI runs a observational campaign, and this is to look at the highly temporal variation. So we have a buoy sitting on the landfast ice up there, and this is a 5-day measurement, and you can see that on a daily basis the temperatures varies by 5-10 degrees. depending on the weather. I assume that the largest differences is when there's sunshine, and therefore you have a large variation. And then you can see as soon as you get just a little bit into the snow, a few centimeters, this variation is more or less gone. So you have a constant temperature. And this is what the issue is when you have floating buoys around where you have weather, putting snow on top of them and all other kind of things. And that can of course also happen here, but this is a little bit more controlled area because the ice doesn't move. But it's important to remember this variation. Also, when we look at the satellite temperatures that are often on a daily basis. So then we have two types of model, essentially. It's the same physical models. There's no real differences. If you take the climatologies, ERA 5, for instance, then it's an atmosphere model. It gets the ice cover from the observations, OSISAF, or some derived observation. And then you have the climate models, which are a fully coupled system, means that they have an ocean and ice and snow and all the interactions in between. They don't simulate the day-to-day, but they try to simulate the climate, the present climate or the future climate, and then you can compare them, look at trends and all other things. And what's important here for the ERA 5 is that they assume a constant ice thickness. There's no snow on it when they calculate fluxes, and that's one of the primary reasons why it has the biases it has. And that means that because when you look at the ocean, it all has a more or less fixed temperature. It's around the freezing point, no matter when, and then as long as it's ice covered. And then then the snow, on the other hand, that insulates towards the atmosphere, and the atmosphere, at least in winter, is often cold compared to. So you have this temperature or energy flux in through the system, which depends on the state of the ice and snow. And that's not really well modeled in ERA 5 and other Reanalysis. So if we continue to look at, this is the way climate models work. You have a number of ensembles, a spaghetti plot, if you like, and then the black line in the middle. I don't know if I can. Well, there's a black line in the middle, which is the ensemble mean. This is actually very close to all the observations below. So the DMI-SIG, that's a OSISAF alike product that Pia has produced together with others. And then you have ERA 5, which uses the ice cover from OSISAF. And you have NSIDC and GHRSST and OSISAF 5, all of them based on passive microwaves. So they agree pretty much. There are some differences, but in large terms they agree. And luckily they agree with the ice extent of the ensemble mean of the climate models as well. If we then look at the surface temperatures of different climatologies, then you can see the warm bias of the ERA 5 first. Other climatologies, I won't touch upon those, also have biases. This is work by Chen, my colleague. I will only focus on ERA 5 because that's normally accepted to be one of the best climatologies existing, and but it's also well known that there are these issues. Then I've tried to split so this is a difference. So you have the ERA 5 on top, and then you have the CMIP runs, which is a climate model seen before. And it's clear that the biases in the CMIP different decades are different than above the ERA 5, and it's smaller. But still remember that this is only the case for the ensemble mean. It's not necessarily the case for the individual runs. And that can be seen on the next one, where the trend, I think that Pia talked a little bit about, where the observations have a little bit larger trend than both the ERA 5 and the CMIP runs. But you can also see all the gray ones, that's the surface temperatures from the different climate models. So they also spread a large variation. Yeah. Okay, so now I've said a few things about the different model systems, and then also, but also on the how the different observations get into play. So it's of course nice to be able to compare, but it would be even nicer if we can correct what we do and see do we get meaningful corrections in the other parts of the system, not just its temperatures. Some of the challenges here is that the ice surface temperatures are only valid daily as a 72-hour mean, at least in the experiment that I got at the time. And that, of course, covers some of the variation that was seen in one of the first plots where we had the high variable surface temperatures. So we need to do something in this. And then the different forcing fields have different frequencies. Yeah. So, and we've also tried to look at that. The data set is a combination, or the observed data set is a combination of MODIS and MET and IASI. We ended up excluding IASI at the time we ran it because we could see there was some, it distinguished itself a little bit from the others, and it also had some positive temperatures in summertime. So we skipped that, and these time series is from just North Greenland. The model system we applied to is DMI HiCom size. As you can see, this is an yearly animation with 5-day snapshots, and you can see how the ice surface temperature varies a lot faster than the sea surface temperature, and also that the summer temperature is very close to zero, which is where it's approximately melting. Yeah, and it simulates the evolution of the sea ice state, the thermodynamics, based on 4 vertical layers plus 1 snow layer. And it's around 10 kilometers. And all experiments are from the period from 12 to 13, summer to summer. And these are the 4 experiments we ran. The aim was part 1 to see the pure effect of the ice surface assimilation. Point 2 to see what happened if we added to the already existing ice concentration assimilation. So we tried to split it in 2 different parts and to have the effect of both. So what was done was that the ice surface temperatures is not directly let's say a derived parameter in an ice model. But we assume that the difference would be around the same as the 2-meter temperature. It's not entirely correct, but it's there's a flavor of it. So we corrected the 2-meter temperature by the difference in the ice surface temperature, knowing that there are some uncertainties, but it still gave us the spatial variation, and it gave us the temporal variations in the 3-hour atmospheric forcing by interpolating back and forth in the different frequencies. And it gave us the colder atmosphere that we expect based on this. Yeah. So what happened here? So here I looking at the model and the observed ice surface temperatures or snow surface temperatures, and it's very clear that the temperatures in both September and March are much colder, and in the observation, and that is reflected very well by the surface temperature of the Aero 5, which is forcing the system. So as long as Aero 5 is that much warmer, your surface will also be warmer than the One thing that sticks out, so that's the before gyre. I'm not entirely sure why, but maybe the state of the ice looks more like what's in the assumed era 5, because that one doesn't have the same difference in March at least. Then the correction is only applied where there's more than 85%, and the first column, that's the interim initial forcing, and then the middle column is where we don't assimilate with ice concentration, and that's where we assimilate with ice concentration, and the last one is where we don't. And that's the reason why there is in the upper second panel is a small area north of Greenland which is being assimilated, which is being corrected, and that's not the case in the last one. That's because the ice concentration is just around 85%, and it's higher in one and not the other. Yeah. Then start to look at the ice cover in July. I'm only covering for the ones where there's no ice concentration assimilation, because that would sort of imply that it's constant. So these are 2 runs with a correction of the 2 meter temperature and the difference. And it's clear to see that in along the Canadian coast and the up towards the Russia, there's an increase of sea ice, and that's the same place where you can see that the concentration is lower. The black contour, that's a 15% OSISAF. So it adds ice where it can add ice, which is expected. Then when I look at the thickness, there's on the left, it's with ice concentration, and that's one of the artifacts that is described by, among others, Greg Smith, that sometimes by assimilating the concentration, you can get an added thickness. So the 2 to the left both have more ice than the ones without the ice concentration assimilation, but they still see an increased thickness, especially near the Canadian coast and archipelago, and this is even further, even more pronounced in the one to the left for me, which is the one where there's no ice concentration assimilation. So the temperatures have a bigger effect here, and that also makes sense because the ice is thinner. So the thermodynamics will add more ice if you change the temperatures. Then looked at a buoy, and note that this is just one buoy that has been extracted from the system, and the top plot, that's from so it has thermistor string into the ice, and the bottom, that's okay. I should have. There's a thermistor string with a temperature measurement every second centimeter, whereas the model only has 4 layers. So they've been averaged. And then there's also the fact that the buoy moves around on the same float. So it has a Lagrangian flow where the buoy is more, the model has individual grid points, and then it just selects the closest grid point to that particular position in time and space. And if we look at a seasonal change, then the top one, that's the model, and it's very distinct that it has a slowly increase in snow, first of all, where the buoy experience a more rapidly changing snow cover. And at the same time, in midwinter, the buoy experience a much colder temperature, again, due to the forcing from the atmosphere. It's also clear that the further down you get, the less affected is the temperatures of the ice and snow, which is what we want to see. Then, when we look at the temporal, the differences on the evolution in the ones with assimilation of not bias correction, then one thing to note is that that's a lower one, the snow cover in the end of the season is much better, and that also produces much smaller vertical biases. But in the middle of the season, it's actually not. It's more the contrary, that it becomes too even less. The difference is bigger. That's the lower one compared to the upper one. It's as this is the in situ one buoy, then it might be expected that you didn't get all the benefits for this particular position. But it's just to look at what happens in the vertical as well when we do this. Yeah. And to conclude, so drifting buoys is a ground truth, but they're also hard to include because they experience a harsh environment. And Reanalysis product have a warm bias, especially Aero 5. We hope that's fixed in Aero 6, where they do a full coupled system. And compared to the CVP6 runs, the temperature bias is bigger, at least compared to the ensemble. And if one wanted to assimilate, I would strongly encourage to go to a level 2 product, because with such a big change in your surface temperatures, it's really important to have the exact timing of your observation. And yeah, and the compared to that one buoy, the snow cover is improved in the end of the season. That's not necessarily a general feature, but at least here it improved the temperature profile. And then at last, Sankare et al. has done a study who used an AI model to do this bias correction, and he found that using the state of the ice, the long wave radiation, and the difference in temperatures would improve. And that makes sense that the state of the ice and snow is one of the problems in Aero 5. Then including that in your correction method is a valid thing to do. So yeah, thanks for your attention.
Consider that we have still a couple of minutes. If one short question now, otherwise you go directly to the question time at the end of the 3 presentations. If this is the case, we will go to the next presentation. This is by Vasily Korabel about use case of improving the Copernicus main service Baltic Sea model produced by assimilating satellite SST.
Conclusions. Not even mine. Slides. Yeah. Hi. So my name is Vasily Korabel. I'm from same institute, Danish Meteorological Institute in Copenhagen, and I will present the use case of improving the Copernicus marine service SST and other variables by assimilating the satellite tests. And for those who are not familiar, what is the MFC is? It's a monitoring and focusing center. The global ocean is divided into the regions. The global ocean is modeled by the Mercator Ocean International, and there are several regional centers that run the regional models. For example, Arctic is run in Norway. Northwest Shelf is run in UK. Now it's moving to Germany. And by coincidence, we were chosen to run the Baltic Sea. That was fortunate. So we are developing. Yes. I think let's skip one slide. Okay. Our MFC produces both near real-time products and the reanalysis. And we are several institutes, so we split the tasks. Right now, the operational center is located in Sweden, and it produces the daily forecasts of physics, biogeochemical variables, and the wave. The wave is actually run in Finland. And we are responsible for the multi-year products of physics and biogeochemistry. I should mention that out of those products, then we can derive the marine ocean indicators, such as the marine heat waves, and all of these products you can find on the Copernicus website catalogs. Different slides. Okay. So this is their schematic of their both near real-time and multi-year production systems. And we really emphasize that we are trying to harmonize both systems. So for the user, the only difference between near real-time and multi-year reanalysis would be the atmospheric forcing. For the near real-time system, it comes from the operational atmospheric model. For the reanalysis system, it comes from the RF5 and the boundary conditions that, in our case, it comes from the Northwest Shelf reanalysis, and for the near real-time system, it comes from the Northwest Shelf near real-time system. The modeling components, data assimilation components are identical in both systems. So here's the area that we model, and in red box, you can see that our product area. So in reality, we have a larger domain that because we have to get the inflows into the Baltic Sea or the salt water from the North Sea. And we behind our physical component, we have the NEMA model, which is right now it's NEMA 4.0. We are upgrading it constantly, so it's going to be NEMA 4.2. When we run at very high horizontal resolution at 1 nautical mile, which is about 2.5 kilometers, with 56 vertical layers. And we produce in Copenhagen, we produce a reanalysis from 93 to 2023 right now. And we assimilate basically everything we can get. So we simulate for the in-situ, we assimilate temperatures or salinity profiles coming from CMEMS catalogs, from ICES, from Shark database, which includes, in recent years, we include also Argos and floats, and we also simulate the biogeochemical profiles, for example, oxygen, nitrogen, phosphate, and we simulate also ice charts. And that helps to improve the physics a lot. For example, you can see that compared to the previous reanalysis that we had before, we greatly reduced the deep biases in the system. So we tracking the observations a lot more closely, which is the key for biogeochemical variables as well. So we better model biogeochemistry because of the improved physics. And in terms of satellite, we assimilate level 3S products from the Copernicus catalog, and the near real-time system assimilates, obviously, near real-time products, while the reanalysis assimilates the reprocessed level 3S product. And Why do we need to assimilate anything at all? It's because the models, when they run freely, they obviously have errors, which has to be corrected. For example, the Baltic Sea model that we have exhibits the negative bias in SST in winter, which means that the model is cooler than the observations. And in summer, we have both positive bias in the North Sea and light negative bias in the Baltic Sea. So we have to reduce those biases, and that's why we simulate their satellite products. But we came with a surprise that when we assimilate level 3S into the near real-time system, we found that the model compared to the observations that we assimilate exhibits positive bias now. And that was a little unexpected. So we checked how this compares to the reprocessed level 3S. And it turned out that the bias features are different. This is the monthly mean for May 2023. And the reason why is because the near real-time product and the reprocessed product happen to be offset by approximately 0.4 kelvins, which is quite big. It's on the order of our model error running freely. So we really have to be careful what we assimilate and what we are comparing to. So that was one unexpected prize that we got. But as I said, our center in Copenhagen produces the multi-year product, and we assimilate the reprocessed product. And how can we check the results? We compare against the level 4, which is also produced in Denmark, in our institute. So the level 4 is produced out of level 3S. So it's not quite independent, but it provides the like first-hand results, and we can check that the model bias is still there. We reducing the biases, but it still has a seasonal SST bias, which is much smaller than in the free model. The root mean square error is generally small, below 0.6 kelvins, and the standard deviation of the temperature is consistent with observations, which is very important. But we can also compare to the in situ observations, which we haven't assimilated, and those are the coastal stations. So I should emphasize that those observations were not assimilated and comes from the independent data set. And we can see that overall we have a slight negative bias consistent with the satellite SSTs. The root mean square error is below 0.7, and normally the correlation scores are like around 0.7, 0.8, which are quite good. So when we assimilating the level 3S and comparing to level 4, what we are looking for in the products is obviously the low errors, spatial and time consistency, but also how the products represent the sharp gradients. For example, fronts of the SST, which you can see that this is the winter in Kattegat. There is a sharp front of the SST, and on the top left, you can see that the level 3S product observes this area quite poorly because of the cloud cover and also presence of ice. The level 4 product, it's a gap-free. It has gaps where there is ice, but otherwise it gets this front quite okay, but compared to their model, it looks very smooth. So the reprocessed, the reanalysis on the bottom right shows that this front is much more variable. It has more meandering features and eddies developing. So the level 4 is a good product, but it's very smooth. So which might, yeah, we cannot assimilate level 4. Therefore, we have to still assimilate level 3 products. So what can we compare our SSTs against? We have another centers producing the level 4 SSTs. For example, the Ostia analysis, which is also level 4 at comparable resolution, 0.05. And in addition to assimilating the satellite sources from multiple satellites, it also assimilates the in situ and ice charts. And it also has the advanced data assimilation scheme. So it uses the NEMO-VAR, the 40VAR system, and it has this NEMO-VAR error covariances, which helps a bit to improve the spatial scales. So if we compare our reanalysis to the Ostia and to the level 4, you can't say which product is better. So both, especially monthly mean maps or seasonal mean maps compared to the error standard deviation, which is quite similar. But if we have a look at the spatial gradients of the SSTs, on the left, you can see the spatial gradients of the level 4 from BMI, and it has a gradients which are a good magnitude, but they are very spatially uniform, which was a bit unexpected. The Ostia gradients in the middle, they are quite consistent, what we expect, where they should be, but the magnitude of those gradients are quite low. And our reanalysis on the far right has gradients which are right magnitudes and in the right locations where they should be. So I think that brings me to the conclusion that both near real-time systems and multi-year system benefit from SST assimilation. You just have to be careful what to compare with. Level 4 SSTs provide very good insights with no gaps and good time consistency, but they are challenging in reproducing SST fronts, positioning of eddies and upwelling regions. And reanalysis offers the alternative view to the level 4, providing the gap-free SSTs consistent with the other variables, for example, sea level and currents. And it's worth looking at alongside with the level 4 system. So I think that. Okay.
Thank you for the presentation. We can move directly to the next talk, which is by Christine Iversen about assimilation of infrared sterilized sulfur temperature retrieval into MET Norway ocean forecast model.
All right. Yes, I can hear that it works. It's some echo, but I guess it's okay. Yeah. Okay, let's see if we find. That's my name. Yes. So hi, everybody. My name is Silje Iversen, and yeah, work at MET Norway. And yeah, Today I will present to you about the assimilation of infrared satellite sea surface temperature retrievals into the ocean forecast model that we use at MET. And the domain you can see in the figure there, that's the model that we used. It's called Nordkyst, and it covers, you see Norway there, and it covers then the coastal current. You have the more shallow regions to the north and south, and then going towards the west, you have more deep regions. All right, so the outline of today is that I will first present to you what data we actually assimilate. And then I will go through that we bias correct some of the sea surface temperature products before we assimilate them. And then in the end, I will show to you what happens if we assimilate diurnal warming events, or if we ignore the diurnal warming that's in the model or in the observations. Okay, so this is then the list of what we assimilate. We assimilate level 2 products, quality level 4 and 5. And the list is shown there. It's the infrared that I listed. So you have MET B, N20, NPP, and Sentinel, 3 and A and B. Yeah, so let's just start with the bias correction that we perform. So before we assimilate the observations, we perform an offline bias correction. And why do we do that? Yeah, as we have talked about, or someone has mentioned here earlier, there are difficulties concerning the sea surface temperature retrieval process. You have, the cloud screening and atmospheric corrections. And also, in addition, you have different data creators that maybe use different algorithms to retrieve the sea surface temperatures. And all of this can cause that the sea surface temperatures from different sensors are subject to regional and temporal biases. And now the question is, why don't we want this when we assimilate the data into the model? Okay, so imagine you see the box or the model up there, and imagine that you have two different satellite products that you are assimilating at the same time and space. One of them is 15 degrees Celsius and the other one is 15.5. And said simply, the model will then become confused because you are trying to assimilate two things at the same time with different temperatures. So we don't want the ocean model to retrieve inconsistent information. And that's why we bias correct. And then how do we do this? So we use a similar bias correction as in this study here. The bias correction is an individual step while we prepare the observations. So it is thus very easy to apply, and we can make changes or modifications to it very easily since it's not in the 4-divar algorithm of our ocean model. The bias is also calculated independently for all products, and we use Sentinel 3 A and B SLSTR sea surface temperatures as the reference. Only quality level 5 here then. Okay, so I will show now an example of how we produce such a bias, and it's a MET B example. So the first step is that we, both for the satellite in question and for the reference, we calculate a daily mean sea surface temperature. And yes, so we do that by averaging all of the passes, all of the swaths within a day. Step number 2 is then that we subtract the daily mean SST for the reference from that of the satellite, so here MET B, to create a daily difference. And as you can see, there are a lot of white spaces in this daily difference field. And to get rid of that, we calculate then a mean bias, which is an 11 days running mean, shown in step 3. Okay, so the last step is that we then regrid this product to the model domain of ours and apply a smoothing filter. So the field shown in step 4 is then what we use to bias correct here the MET sea surface temperatures at the current day. Okay, so the question is then, does this work? Will it improve our model results? So what we do is that we run 2 different data assimilation experiments where we assimilate MET SSTs and N20. The experiments are called, as you can see in the table, IR1 and IR2. So in the first one there, IR1, we have turned off the bias correction. And in the second one, we turn it on. And then, in order to see if the model SST improves, we validate first against the satellite sea surface temperatures that we didn't assimilate. And as you can see, the RMSE and the bias of the model SST reduces, going from IR1 to IR2. And that is good. But we do also expect this result because the satellite sea surface temperatures used as reference, they are not completely independent of those assimilated. But what we see also, if you use other references, in situ sea surface temperatures from drifting buoys, is that we get the same result. The bias and the RMSE of the model SST reduces when we turn on the bias correction. So that is good. Then we know that we have done something right. Okay, so then let's go over to the next topic, which is diurnal warming that's in the sea surface temperature products. So this is a typical illustration of diurnal warming with the buildup of the warm layer and the peak temperature at the millimeter scales. And the sea surface temperatures that we assimilate, right, they catch this peak warming. But our ocean forecast model cannot represent this large warming because the sea surface temperature in this model is the sea surface temperature at 20 centimeters to more than 1 meter down into the water column. So there is clearly a mismatch. And if we want to assimilate the products, special care is required so we not end up with biased model temperatures. Okay. So the classical approach when we assimilate sea surface temperatures is that we focus only on the nighttime data and that we apply a simplistic filter in order to remove observations, daytime observations where the wind speed is low. But what happens then is that we remove a lot of observations that we could have used. As you can see in the figure up there is an example. It's observations within 15 minutes, and applying the simplistic filter basically removes, almost all of the observations in the domain. And also, that is not only the problem, because in the Arctic, there is not really something as a true night. So when we are applying the simplistic filter, what actually is the daytime data? How do we define the daytime? So there are some questions that we have, but before we do more study on this topic, we ask ourselves what actually happens if we assimilate the diurnal warming. What's the impact on the modeled SST? Okay, so now the method is that we perform 3 different data assimilation experiments. So in one of them, we assimilate the diurnal warming. It's the one there with the label with diurnal warming. In the other one, we do not assimilate diurnal warming. Example shown is the other plot there. And in all of the experiments, we assimilate synthetic observations that we harvest from another high-resolution ocean model. And for this experiment with diurnal warming, we add diurnal warming to these synthetic observations. And the diurnal warming that we add is calculated from real satellite observations. So in the next slides, I will show to you the difference between the model results with diurnal warming and the model results without diurnal warming. So basically, I'm going to show you what happens when we assimilate diurnal warming observations. So this figure shows you the temperature difference then. And as you can see, it's the surface. And as you can see, we have quite some warming along the coast. But yeah, and those regions, they do match the regions where we assimilated the warmer observations. And of course, we assimilate warm observations, so we do expect the sea surface to get warmer. So what is interesting now is to see what happens in depth. So we take a cross section, and let's zoom into this cross section then. Okay, so now you see the surface again, and then you have the vertical cross section there with an arrow showing you approximately 50 meters down into the water column. So what we see now is that even though we only assimilated surface observations, we end up adjusting the temperature like 50 or 60 meters down into the water column in this particular example. So you have you get warmer temperatures in the mixed layer, and then the temperatures become colder below the mixed layers. So what we see here is that the stratification has increased in the model. Okay. So if we look at the mixed layer depth changes, we see that there is a lot of blue color over there, which means that the mixed layer depth has reduced also. And the thing now is that, so we have a lot of stratification changes occurring in the model, but these stratification changes, they do persist in the following forecast. So later in the model, they are still there. So, and that happens also even though there is no more diurnal warming observations assimilated at these locations. So the model kind of remembers this warming, even though we stopped assimilating them. And that is not good because that will follow in the next forecast and so on. So we now know that we need to continue using diurnal warming removal methods like this simplistic filter, even though we lost so many observations. And what's nice also that is that this study shows that this does not degrade the model results. I haven't shown you that, but yeah, we know that that's not an issue then to remove the observations. And that's all from me. Thank you so much.
Thank you for the presentation. We can move to the next one. Which is the question time. Sorry, I forgot that. Okay, we can start with the first question. Ready?
Hi, Andy Harris, University of Maryland. It was a bit where I kind of missed. What did you define as diurnal warming? Was it just the wind speed, or was there something more sophisticated?
You mean when I removed observations?
Yes.
Yes, then it was daytime observations where the wind speed is low.
Okay.
So we remove it in order to ensure that we don't have the big case.
Yeah. I mean, the thing is that that's a very crude way of doing it. As it happens. So depending on the time of day, you know, so if it was in the afternoon and less than 5, I would say, yeah, okay. Although in fact you had a threshold of 6, didn't you?
Yeah.
In fact, which is, you know, the average ocean wind speed is what, 7.4 or something. So that's understandably in the summer, you're going to massively reduce it. The problem is, of course, that you essentially, when you've got, say, a Kelvin warm or something like that, you end up propagating it down to the base of the mixed layer in your model, depending on how you assimilate it. And then that's buoyant water that you can't easily convect out and get rid of. And so I would suggest maybe trying to, if you want those observations back again, you probably need to actually calculate what the diurnal warming is and remove it before you assimilate it, rather than, or at least run a model that estimates how much diurnal warming you actually have, because diurnal warming at 2 o'clock in the afternoon, okay, fair enough, there might be a bit, but if you go at sort of like 9 o'clock in the morning or 9:30 in the morning for METOP, there would be much less diurnal warming. So
yeah, and I totally agree with you there.
Yeah.
And that's kind of the questions that we had. Do we have to do something about this? And then we didn't even know how much did it impact the model. So that's why we ran those experiments to see, does it do something to the model, or can we just use them? even though, yeah, they should be removed by the threshold. But we figured out that, yeah, we can't use that. And as it turns out, we have so many sea surface temperature observations that it didn't seem to degrade the model that we actually removed them. Yeah. But that can be only for this particular model or this data assimilation case. But like the RMSE and the bias was the same as when we removed them as they were if we had good observations, or I call it good, but diurnal warming free observations instead. Surprisingly, we didn't, understand why, but.
Okay, well, I mean, I guess if it's adding noise into your mixed layer by including them, depending on, then taking it away won't make it worse. You'll just get back to the state.
We had this third experiment also where we assimilated the same, all of the observations, but we didn't add the diurnal warming, So comparing this with the experiment where you removed everything, they gave quite similar results. Yeah.
Yeah. Maybe think about it a little bit more, but okay, thanks.
Kind of off-topic question here.
Okay.
Your model, it didn't include Svalbard, did it? So do you have another model for Svalbard?
Yes, we have a model called Baden. It's not the same. It's not for DVAR. It's the ensemble Kalman filter, but yeah, that's the model that covers the more northern regions. Yeah.
Okay, thanks.
More questions? I have also a question about the simulation of single sensors used in this last presentation. Have you tried to use also composite product like the Siemens product for the level 4?
You asked now if we have tried level 4 products and so on, or?
Yes, no, I'm talking about the level 4 composite product with several sensors already matched together after bias correction, which are available within Siemens, for instance. Yeah, with people doing this.
What after bias correction? I'm not sure I understood.
Okay.
What the question was. If we why we don't assimilate those products instead? Is that the question?
If you use a micro.
No, maybe Salvatore is referring to level 3S product that is merged multi-sensor satellite.
Yes, a multi-sensor product obtained merging all the satellite of a certain day after bias adjustment. You do bias adjustment, but you assimilate each one single sensor, not all together.
Not all together. No. It's the level 2 products that we bias correct and then assimilate.
It's what exactly.
Yeah, at the time that they belong. So that's correct. Yeah.
For the previous presentation, I see that there is a simulation of level 3 data from satellite by another forecast system within Siemens. They use a level 4. Do you know what is the advantage to use directly level 3 instead of the level 4 for the simulation? This is for Vasily, for remember where. Yes, Lisa. The macro is there, Kevin.
Can you repeat the question, please?
Yes, you simulated the level 3 satellite data.
Yeah, we assimilate
instead of level 4.
Instead of level 4.
Why?
Yeah. Well, because level 4 has contains errors because of optimal interpolation, and we don't want to assimilate those errors. Obviously.
So the main difference between the two is that you gap fill with data that is not. You gap fill the data in level 4 from level 3, and you're not really interested in putting climatology or other things into your models.
Yes, I agree. I was making the question just because I know that, for instance, the Mediterranean case, the similar level 4 data.
Yeah, I don't know.
It's MEMS, yes. It was why.
Yeah, I think that's basically using L4 data is much smoother. It's kind of like a daily mean. Then you lost the like daily diurnal variations. In some of the method, I think, but in some method, it actually can capture such kind of diurnal variations.
Yes.
Yeah, that's I think is the main reason.
It's really noisy, but also part of the signal.
Thanks. I mean, the thing about L4 is that you sent most L4s as you're doing some interpolation, some optimal interpolation between valid data points. But if you've got a model, a physical model, then that should be better at filling in because it's actually got physics and advection and things like that. So you'd be better off just taking the raw satellite observations in those and allowing the filling in not to be some statistical thing, but something determined by geophysical fluid dynamics and forcing fields. Should be a better answer. So that's why I would not assimilate L4 into an analysis.
Yes, matter with using physics instead of statistics.
Yeah.
Mm-hmm. Okay, if there are no more questions, we can go to the coffee break time, and we meet again at 16:45.
Carino questo oggetto qua che
Cosa?
inizialmente non avevo capito che questo quando chatta, quando quella roba qui.
Ah,
Inizialmente pensavo quando vecchio chatta, invece era semplicemente il.
c'era il microfono. Bella perfezione.
Quando loro parlano di là, viene qui chiaramente la descrizione. Inizialmente non avevo capito cosa c'era. Questa gente che c'è tanta. Del posto, no?
Cosa?
Perché del gioco fa del fondo.
No, 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 perché siccome non ci vede bene, da lontano ci sono le presentazioni, quindi me le sto scaricate e le guardo da qua.
C'è un template.
No, è questo.
Vedi?
Ah, perché per la presentazione, ok, no, io sto printando del report, sì. Poi lo metto a posto proprio.
Sì, no, anche se scritto in alcuni, di quasi più un po' giorno.
Sì. Sì, te lo volevo sistemare un attimo.
Sì, no, Quando si scritto 2 o 3 ore di sesso, non stiamo a fare qua.
No. Si vede per lo stesso.
Adesso ci.
Okay, it's time to start again. It's 17:10. Next online, yes. Can we sit? We have to start the the last two presentations.
Hello, just to test, do you hear me here?
Yes, seems to be working, yes.
Okay.
So this first presentation of the last section is...
Hello.
Hello?
Can we please sit down?
Just a moment.
Okay.
Okay, this presentation is given by Housseyni Sankare. I hope I pronounce well your name. It's about CP6 SST based correct data for ocean region around Canada.
Yeah, okay, thank you. Do you see there my screen?
Yes, yes.
I'm ready. If you want, I can start.
Let's start.
I can start?
Yes, you can.
Okay. Yeah, okay. Thank you, everyone. My name is Housseyni Sankare from Canadian Center for Climate Services. It's part of Environment and Climate Change Canada. In Canada Center of Climate Service, we provide climate data and services. And then before we provide this data, we ensure the reliability of the data. Sometimes we do some bias correction if it need. Today, I will present here the result of our CMIP6 model SST bias correction for the Canadian Ocean region. And climate change impact ocean ecosystems in diverse ways, altering both the physical environment and biochemical cycles. And then the sea surface temperature is a crucial variable that affects by this change in the climate change. So reliable projection of SST is essential to inform effective mitigation and adaptation strategies. The Canadian Centre for Climate Services evaluated CMIP6 model performance for SST and then applied bias correction to make them available on our climate data portal, naming climatedata.ca. You know, Canada has the world's largest coastline and an extensive marine territory. By the total marine area, approximately 5.75 million square kilometers. This includes the ocean area in the Pacific coast, the Atlantic coast, the Arctic Ocean, including the Houston Bay and the surrounding water. And then the objective for this presentation here, just to show you a comparison of CMIP6 model output bias corrected with OSIA observational data set, and then again make some analysis of SST future projection. For the data and methodology, we used 28 CMIP6 GCMs, historical plus 4 SSPs, and also we use the OSIA data like target to bias corrected with data and also comparing to assess the result. SST bias correction, we done that with the Cantu delta mapping method that we apply to all the 28 models. Each model, first we interpolated them at the 0.05 degree of resolution, that is the OSIA resolution. And then again, we assess the output against the OSIA data. This map here presents the three panels that make a comparison of SST using the OSIA data and the SIMF6 output. On the left side, the left panel shows the annual mean SST from the OSIA data that provide us a higher resolution observational references. And the central panel shows the mean bias of SST from the model median from uncorrected SIMF6 model relative to OSIA that show the magnitude and the spatial patterns of systematic bias, particularly in the Atlantic Ocean here, the north part of Atlantic Ocean. And then the right panels here, it shows the mean bias of SST model median from the bias-corrected SIMF6 relative to OSIA data that illustrating the reduction of discrepancies following the application of the bias correction techniques. This comparison highlights the effectiveness of bias correction with notable improvements in SST representation, especially in the northern Atlantic Ocean, where the raw model biases were more pronounced. And then this histogram presents the mean SST bias of SIMF6 model output relative to OSIA again, historical. And then the analysis is based on the median also for all the 28 SIMF6 model, but for 13 ocean subregion around Canada, what's showing in the map below here. And then we saw here two set of value. In the blue one, we have unadjusted raw model outputs, and the red one, we have a bias adjusted output, allowing for that allows us to a direct comparison of the model performance before and after the bias correction. Across most of subregion, the unadjusted model saw small but consistent positive bias, indicating a general tendency to overestimated SST compared to OSIA data. Once we apply the bias correction, the bias are significantly reduced, which demonstrates that the bias correction method is effectively in improving the alignment of model SST with observation conditions across diverse oceanic regions. And then after that, I done some analysis in the future comparing here the tendencies. The map show the linear tendencies in SST for the historical period, that is from 1970 to 2014, and fitted projection the fitted projection, I take all the period 2020 to 2100 under all the four scenario here. And then you saw that is the historical, just to show the reference. And after that, and that is the first scenario, the second one, and that is the last scenario. You saw here the magnitude of the tendency increase with the emission scenario. Also, the spatial patterns shift with the warming level. Low scenario saw more localized warming ranging For example, for the SSP to 4.8 here, we saw the warming is ranging from 0.2 to 0.4 by decade. And then if we saw for the last scenario, that is the SSP 8.5, for this one, we can see that the warming ranging from 0.5 to 0.8 by decade. That is more for this one. Again, and then also if we remark the Arctic amplification is evident in all scenarios, but become dominant in the two last higher emission scenario, that is the SSP 37.0 and the SSP 8.5. Again, here I saw a box plot of the median comparing the historical and the last century period, that is 2070 to 2100, that illustrated the distributions of SST, but is the spatial mean. It is spatial mean across all Canada and across all scenarios. And then the bar, if we saw for the SSP here, 58.85 here, we are the larger one for the history, indicating a greater variability and spread under higher scenario. Here is a clear progression in SST mean value from the low scenario to the higher scenario, reflecting the model and some sensibility in increasing radiation forcing. This confirmed that SST projection responds to a level of greenhouse gases emission. And then that will be the last analysis here. Is the histogram illustrated a projected SST change between the historical and the last century period based on the median of a model output also, but we model, but we bias corrected them. Again, it for our 13 subregion ocean across Canada, but here I didn't show for SSPs, but just for 3 SSPs, because the change is a little change for the SSPs 2.6 is the change is a light change here. And across all scenario and subregion, SST is projected to increase with a magnitude of change directly linked to the emission scenario. For example, under the SSP 4.5, the projected warming is more moderated with a minimum increase of approximately plus 1.3 degrees C. In contrast, if we look at the SSP 8.5, representing here the higher emission scenario, it shows the most significant warming with some subregion experiencing increase up to plus 4.8 degree. Here projections highlight a consistent warming trend across all Canada marine regions. The results emphasize the critical role of emission mitigation and limiting ocean warming and its potential impacts on coastal ecosystems and coastal communities. And in conclusion of this presentation, this study analyzed the SIMF6 model SST bias correction data in ocean region around Canada The result show is a light SST bias between the model and the ocean historical data in the Pacific Ocean and the Canadian Arctic region, and it saw a notable bias in the Atlantic Ocean, reaching sometime -5 degrees C. But the bias correction effectively reduces model bias as demonstrated by the improved agreement between the corrected model output and the ocean observation. The next step for this project will be to do some user engagement to know the local community and all industries that need to use this data, and then what we want it to be, and then if we need some indexes derived in the SST, we will calculate that and integrate it in our portal naming climate data. That's thank you.
Thank you, Sim, for the presentation. Now we can move to the last presentation for today, given by Maxime Beauchamp. The title is Multiscale Neural Assimilation Scheme for Learning Near Real-Time Level 4 SST Product from Satellite Observations.
Sorry, I'm trying to get back to the first slide. Well, anyway, that's not a big problem. I guess that's okay. Hi, everyone. I'm Maxime Beauchamp from DMI. This is the last presentation of the day. I guess you're all very tired, so I make a very technical presentation so that you can take a nap. No, I'm kidding. This is not so technical. Anyway, so I'm working in Jacob's group at DMI. I'm in charge of developing AI methods to revisit some operational products regarding SST and CIs. Today,